Hello, and welcome to our presentation on the theory, measurement, and guideline limits for rail vibrations on residential buildings. Rail vibrations are caused by unevenness between two surfaces in contact. It can be perceived as both an acoustic and a dynamic sensation. These vibrations are generally perceived through a building or the ground as gentle shaking or trembling. This is known as ground-borne vibration. Ground-borne noise, also known as vibration-induced noise, is defined as noise generated inside a building by ground-borne vibration generated from the passing of a vehicle on rails. Airborne noise is generated by the wheel-to-rail contact as well as the additional equipment on board the train. For high-speed traffic, aerodynamic noise may also be relevant. Ground-borne vibration is generated by the interaction between train, the track, and the subsoil. The vibration is transmitted through the ground and may reach the foundation of a building. Vibration strength is usually measured as RMS, or root mean squared vibration velocity. Light rail trains have an RMS vibration velocity of around 0.06 millimeters per second. Commuter trains have an RMS vibration velocity of about 0.17 to 0.53 millimeters per second. High-speed rail trains have an RMS vibration velocity of about 0.25 millimeters per second, and underground rail trains have an RMS vibration velocity of about 0.25 to 0.5 millimeters per second. Rail vibrations always influence the surrounding buildings and environment, but their impact is dependent on the strength of the signal and the type of rail. The foundation is also an important factor, as some buildings may react to excitation in such a way that the vibration is transferred through the structure. In the cases where minor cosmetic damage occurs, there are often many more credible causes, such as settlement due to fatigue caused by natural aging of building materials, moisture, weather, or temperature variations. It is almost impossible to allocate the damage to any of these potential causes with certainty. The reported cases in which minor cosmetic damages were done to a building or structure had high vibration strengths, reaching a vibration velocity of 5 millimeters per second, which far exceeds the vibration caused by trains, which is typically 0.1 to 0.6 millimeters per second on average. Before construction can begin on or near a new rail system, calculations and simulations must be conducted to ensure that the negative effects of rail vibration are mitigated. In order to develop these models, data must be obtained to determine the water content, density, and shear wave velocity. Some of this data is obtained directly from soil samples, but vibrations in the earth can also be measured using an array of geophones. A geophone is a device that converts motion to voltage. This is accomplished either by using a coil mounted to a spring that moves relative to a magnet, or by a mass elastically suspended with small air gaps on either side acting as variable capacitors. For the study of rail vibrations, geophones are generally configured in 3-component arrays. This means that each array actually has 3 geophones to measure motion in each dimension. All the arrangements shown here are using 3-component geophones. They are simply spaced several meters apart and are often placed at ground level. Sometimes, however, they must be placed below ground. The image on the left is a good example of this, as it represents the position of geophone arrays used to study a subway line. It includes arrays placed in a vertical shaft 12 and 17 meters below the level of the track. The data that is collected from the geophones is usually sent to a data acquisition instrument, which can convert the raw output of the sensors into usable information. It is sent to a PC that can pre-process the data using software such as MATLAB or even Microsoft Excel. After being compiled and graphed, it can then be compared to acceptable levels when developing a new project, or the data can be used to help conduct analysis on other projects. These projects must follow government laws and regulations that protect both new and old buildings. An effective way of knowing whether the rail system will cause damage to surrounding buildings is to calculate the vibration velocity caused by the moving trains in relation to the distance between the rail and the building. Vibration velocity is calculated as shown. damage starts to occur when the velocity levels exceed 85 vibration decibels. According to the United States Department of Transportation and Federal Transit Administration, if the ground-borne vibration velocity exceeds 85 to 100 vibration decibels, damage to surrounding structures is likely to occur. However, it's unlikely that a transit system will exceed 85 VDB unless it's operating at an extreme speed or with an uneven rail surface. Therefore, if a train is operating at normal speeds with smooth rail-to-wheel contact, it's likely to operate within the restricted guidelines. Most commuting rails operate below 85 vibration decibels, thus are no risk to buildings that are further than 50 feet. Each project depends on the surrounding buildings and their properties, and is important for the buildings to be designed for a nearby rail system. If the rail system is being implemented on buildings that were not previously designed for an underground rail system, it is important to consider these factors and the surrounding environmental conditions to determine whether a rail system would be suitable for that area. When rail vibrations exceed a certain limit, mitigation measures need to be taken to try and reduce the vibrations. Measures can be implemented on railways, trains, residential buildings, and the land between the railway and residential buildings. The most effective way to reduce vibrational effects is applying measures to the railway. An important measure to reduce vibration is to build railways on soils that are stiff. The higher the dynamic elastic modulus and shear wave velocities, the lower the vibrational effects. For existing railways, the stiffness of the soil can be improved by mixing binder into the soil. Another measure that can reduce vibration is using continuously welded rails instead of jointed rails. Trains equipped with secondary suspension systems also have lower levels of vibration. Secondary suspension systems and wheels must be regularly maintained to ensure minimal vibrations. Applying mitigation measures to existing residential buildings can be very complicated and it won't be effective. Most measures have to be applied to the foundation of these buildings when they are being designed and constructed. The most effective way to reduce the vibrations on the residential buildings is by adding elastomeric bearings in the foundations. When you have an existing railway and residential buildings nearby, the easiest approach is to apply mitigation measures on the path between the railway and the buildings. To apply the measures along the path, a barrier wall must be dug, usually between 5 to 10 meters deep. The most common barriers used are water barriers, concrete walls, or steel walls. The concrete and steel walls are much more effective at reducing vibrations because they have a higher stiffness than water, but those methods are far more expensive.